Hi guys, this is Mr. Mgara. Today we're going to try to look at the alternating current and voltages, and we're just going to focus on the sinusoidal waves. Now, as I did mention, that the next topic that we're going to start looking at is the series of the AC. So in this series, I'm going to talk about the alternating current and voltages, and we're just going to try to familiarize ourselves with the sinusoidal waveforms. Alright, so let's get it to the next page. Now, what we're going to look at, we're just going to discuss the characteristics of a sinusoidal wave, define the mathematical relationship between the period, frequency, and angular frequency of a sine wave, explain how to define the amplitude of a sine wave, describe what a phase angle is and the difference between lagging and leading signals. Now, when we talk about the characteristics of a sine wave, the length of time it takes to complete one cycle, or conversely, the number of cycles that occur in 1 second. Right. So, in association with this, we have these terminologies that you guys need to really understand, because you remember that when we talk about AC has to do with a sinusoidal, specifically voltage waveform in this case, that changes with time, and apparently there are terminologies that are very important for us to understand before we dive into the details. So for example, we have what we call the period, we have the frequency, the angular frequency. These things need to be understood, and the maximum and minimum voltage or current swing. We have also what we call the amplitude, the peak-to-peak amplitude, the value of the root mean square values, the RMS. We also need to understand the average value of a sine wave. Okay, so the DC offset. We also need to understand the comparison between two sine waves, the phase angle, the lagging and leading signals. Now, these things are really a characteristics of a sine wave, which in this case happens to be the reference for how these voltages and currents are produced. Remember that they are produced by generators, and these generators, they produce currents and voltages that are alternating in nature. And the perfect description of how these voltages and currents should be, they should actually be in a sine wave format, which is the signal that we're going to look at. So now, for example, here you can see here that is a voltage and it's actually plotted against time. This is really how an AC voltage would look like. It will actually be swinging, right? Now we all know that, so we're gonna have to look for things like the period. Now the period could just be something that ranges from 0 to somewhere here, or you can take between two successful crests which are there, or between two successful troughs. That actually forms your period. So if I take from this 0 to somewhere there, alright, then this is really my sinusoidal, and it gives me my period. Now of course we can look at things like that. We can see that the time that it takes for a sine wave to complete one full cycle, this can be measured by finding the times at which the signal crosses the 0 to 0 crossing. So the unit usually used is seconds, right? So you can see here that we can look at between two successful crests. We can take that as a period, but other than that, we can also take that from this 0 crossing to that 0 crossing. That becomes my period. And if I can equate that in terms of time, of course, that I can get that as my period, and I can also, if I put that over, like here we have T1 minus T2, it's about 150 milliseconds, and that 150 haves, that comes to about 20 milliseconds. So that's how this signal would be characterized in terms of period. But I want you to also understand that this is a sinusoidal voltage waveform, and actually it's changing with time. And you can see, as we can see here, now we're going to be discuss the 377 because this has to do with your angular frequency. And this of course becomes the amplitude. As you can see here, there's 5 volts, and that's exactly the 5 volts, which is the maximum value. And this is the sine wave that the voltage profile follows. Now the number of cycles a sine wave will complete in 1 second. A fraction are called fractions are okay, so the unit is cycles per second or hertz. So that gives us the frequency, which is the number of cycles the sine wave will complete in 1 second. So the longer the period, the lower the frequency. The shorter the period, the higher the frequency. And we know that frequency is 1 over period. And if we have something like this, and that gives you about 60 hertz. Right. Now, if we look at the electric utilities, standardization on the frequency of electricity distributions didn't occur until the mid-1900s. So the frequency of the AC voltage supplied by power companies in the US is about 60 Hz, most of them. So the frequency used in much of the European countries and Asian and even African countries about 50 Hz. While some electronic circuits function properly when connected to the AC to a power supply operating at either frequency, some are designed for specific, which is one of the reasons why power adapters are needed when you travel. Right? If you look at the label on the laboratory, the frequency of the AC signal is specified. Right? Now, motors, when we talk about angular frequency, then we're dealing with things like we need to understand, for example, motors are used in alternators, in coal and gas-powered electric generation station. One full rotation of a motor shaft produces one complete cycle of an AC electric circuit. So position of the motor shaft is measured in radians or degrees. So the position is measured in radians or in degrees. And we're saying that 1 rad is about 557.3 degrees and 2 pi rad is about 360 degrees. And so this angular frequency right here is giving us 2 pi f or 2 pi over t, because 2 pi over t is exactly 2 pi f because of 1 over f. And if the frequency is 60 Hz, then definitely the angular frequency is 3.777. So meaning that you multiply the 2 pi, you multiply it by f. Alright. Now there's some terminologies also we need to understand, such as amplitude, for example, right? So we know that this actually refers to the amplitude. So this is the sinusoidal waveform, and that's what it is. Its amplitude value is 5. And these things you need to understand. And we can also take a distance between this point and that point, right? And that becomes the peak-to-peak value, the VPPP. And VPP is actually twice the peak value. So we can also have the IPPP, which has to do with current, and is twice the amplitude value. Now guys, we also have what we call the instantaneous values. Now instantaneous values have to do with instantaneous value, or amplitude is the magnitude of the sinusoidal at a point in time. So when we say that this voltage changes with time and then it follows a certain sinusoidal signal, then we have what we call the instantaneous value. Now believe you me, we've already mentioned that this is VTT. We're saying 5 over 5 volts. This is the amplitude. Sine omega, now this is omega, which is your 2 pi f, which is measured in rad per second. And we can say that times time, at this time we can say, for example, if we have this is as a function, this is omega already t, right, and it's measured in rad per second. We can say at time equals 0, we can replace the 0 there, and we can say that time equals 0, the instantaneous value is 0. And at time equals 10 milliseconds, so you have to change that to seconds, and that gives you about minus 2.94. That's just the instantaneous value, or amplitude is the magnitude of the sinusoidal at a point. Now of course we have things like the average value of a signal. Now if you look at this signal, really the average value is 0, because when you integrate over this period, you find that this shade right here is actually equal to that. So this would definitely give us a 0. If the average of an AC signal is not 0, then there is a DC component known as a DC offset. So if the average is not 0, then there's a DC component which is called the DC offset. Now the root mean square value. So most of equipment that measure the amplitude of sinusoidal signal displays the result as most of this equipment that measure the amplitude of sinusoids display the result as a root mean square value. This is signified by the unit VSC or VRIMS. Alright, so most of the equipment that measure amplitude of a signal displays the result as a root mean square value. So most of these nameplates you find that they'll display the root root square value. And what is this root square value? So the RMS voltage and current are used to calculate the average power associated with the voltage or current signal in one cycle. So if you look at how do we calculate the VRMS, well, that's the formula right there, which is the square root of one of the period of a given signal, then you square it and you get that. So the VRMS can also be expressed in terms of in terms of the square root of 2 divided by 2 times the amplitude value, which is Vm, or Vm over 2, and that actually gives you about 0.703 of the amplitude, and we can use this to calculate the power using the VRMS squared divided by R. Now the phase angle is an angular, so now another very important concept is the phase angle. So the phase angle is an angular measurement of the position of one sinusoidal signal with respect to the reference. Okay, the phase angle is an angular measurement of the position of one sinusoidal with reference to the reference. The signal and the reference must have the same frequency. So now for example, I just want to show you how we do our calculations of these phases, right? But before you understand the concept of phases, guys, we could actually look at what are some of the, for example, what we mean when we talk about the phase relationship. Now, a phase is simply a shift, right? So if you have got omega t, which is the main function, but then you may add a plus theta there, which gives us a shift of the sine wave with reference to a certain reference point. So usually the reference point is the 0 point. So for example, we can say that adding angle phi to an angle of this in the sine function, like a sine function like this, causes the sine waveform to shift either to the left when we add a plus, or we can cause it to shift to the right when we subtract. Okay, so guys, you need to remember these points, because when we add, it means we are actually shifting the sine wave to the right, and when we to the left, sorry, and when we subtract, we're shifting the sine wave to the to the left. So for example, if we have two voltages, we have got this voltage, and that Vp is simply the amplitude, and of course you can see that the this waveform of voltage is actually shifted to the to the left. And you can also see that when we have a sine wave, we can see that it's just got the amplitude, and also we can say that this is also shifted to the left. Now omega is in radians, as we may see, but theta is expressed in degrees. Alright, so for example, we can have 5 sin omega is means that this is shifted left by 30 degrees, right? And you can do your math. For example, find the instant value at t equals that if this is shifted by that, and the answer would give you that. Now let's just try to visualize what this concept of lag and lead, what it is all about. So for example, if we take this 0 as our reference point, of course we can also see that it's not difficult to see that with reference to the 0 point, we have this waveform right here, which is the dotted one, which is the current. Actually, with respect to the 0 crossing, it's like shifted to the right, and then we can see that's minus 50. And we can also see that the voltage right here, which is you can see right there, is with respect to this 0 point as our reference, it is actually shifted to the right, and that's how come to the left, sorry, and that's how come we add a plus in terms of the sinusoidal, in terms of the alternating instantaneous voltage waveform. So Vt is shifted to by 30 degrees, that is shifted by right by 50 degrees, Vt lies to the left by 80 degrees. Now if we take this signal as our reference signal, then definitely we know that this guy of this voltage is leading this voltage by 80, because then though our reference is this, we're saying if with reference to this one, it's actually lagging by 80 degrees. Notice how Vt reaches the peak of value 80 before the phases comparison of this type can only be made if two waveforms have the same frequency. Guys, remember, if these are all running at a particular frequency, let's say 50 Hz, or If it is 10 Hz, then this is a valid assumption. Now, phase comparison of this type can only be made if two waveforms have the same what frequency. Now, if you have that and you have that, I1 is shifted to the right by 18 degrees, and I2 is also shifted to the right by 31 degrees. I1 lies 31. So if we check this here, we can see that this guy is shifted to the right by 31 degrees, and this one is shifted to the right by 31 degrees. We can also say that I2 shifted to the right by 31. I1 lies, so if we see that I1 lies 31 minus 18 to the left of I2, and that's really understood. So if we try to get them as their own reference, we can just subtract. For example, since this guy I1 is this and that is that, so if we subtract, this one is a bit on the right side, is a bit actually on the left side than that one. So if we subtract, we can even say, okay, with respect to this one, I1 lies 31 minus 18. Okay, and we can also conclude that in this case that I1 leads I2 by 13 degrees. Now guys, you need to keep this. It's very easy to understand, and just understand that there's this concept of lagging, and in this case we're taking this 0 as our reference, and if that is our reference, then this guy could lead by 30 degrees with respect to this, and this guy, if this guy is lagging this by also 50 degrees, we can actually specify that. But with respect to each other, you can even see that voltage is actually leading the current by 80 degrees. Alright, so we can also do the writing of formulas, which is actually very important right here, guys, because then now we have the voltage waveform, which is the instantaneous voltage waveform, can actually be expressed as the amplitude voltage, the sound wave, and we can maintain our omega t, which is our 2 pi ft, and then plus the theta. So now what this simply means is a general formula that actually gives us how the waveform actually is actually expressed. So it can be expressed in terms of the phasor, and if this theta is 0, then therefore it will just be b sine omega t. Right? If it's not there, or if it's there, if it's 0, it can be like that. If it's something where the signal should lag, then it should be a minus there. So where theta is in degree, and units for omega usually not included. Right? Now, what is the summary of all of this? So AC signals are sinusoidal functions, and we need to understand that the mathematical description of the sinusoid includes the peak value, the amplitude, and the angular frequency, and may include a phase. So we can see here that this is the angular frequency. We can also look at the VRMS, which can be calculated as root of 2 over 2 times VP, or VM over 2. And that gives us, in this case, of course, it gives us the VRMS value. So RMS value of a sinusoid are calculated using the formula, and phase angle is calculated with respect to the reference. Phase angle is calculated with reference, and we've seen all of these references right here. So the VRMS here is, we can see that this is the formula that we use, and this is also the formula that we use to characterize an AC signal. Thank you so much, guys, and I'd like to thank you for this little summary, and we're gonna show you in the next class when we start diving into the details. But this was a short introduction to give you a clue about the AC voltage and current, AC voltage and AC current, sinusoidal waveforms, and also to try to pick out some of the technologies which are very, very much important for performance. So I'd like to thank you guys. God bless you, and I'll see you in the next video.